The stable roommate problem is the problem where there are some even number of people who need to be matched together in pairs, for example as roommates. The problem assumes that each person involved lists each other person in order of preference. The problem is that of finding a stable matching, such that each person has a partner at the end and there are no two people who aren't matched, but who would prefer each other over their current partners. This is similar to the stable marriage problem, which you might have heard of. The difference is that there is only one group involved, of which every member is allowed to propose to any other member. A consequence of this difference is that for some sets of people and preferences, a stable matching is impossible. Irving's algorithm is a solution to this problem. The algorithm determines whether a stable matching exists, and if so, will find such a matching.
As an example, here is a table showing 6 people and their individual preferences, listed from most to least preferred. Note that there has to be an even number of people for a full set of matches to be found, and that each member must include all other members of the group in their list. In the first stage of the algorithm, each member of the group proposes to their preferred matches in turn. They will be rejected if and only if the person receiving the proposal is already holding a proposal from someone they prefer. The proposals will go on until each member holds a proposal from another member. In our example, A will begin the proceedings by proposing to its top preference, B. As we can see from the proposal table, B does not currently hold a proposal from another member, and so it will hold A's proposal. Next, B will propose to F. Note that the fact B is currently holding a proposal from A is irrelevant, as all members must make proposals of their own to find their best stable match. Again, F does not currently hold a proposal, and so it will hold B's. C will also propose to F, but F already holds a proposal from B. From looking through F's preference list, we can see that F prefers its current suitor, B, to C, and so F will reject C's proposal. C now moves on to the next most preferred member on its list, D. As D isn't holding a proposal, it now holds C's. After D successfully proposes to A, E proposes to D. D currently holds a proposal from C, but it actually prefers E to C, and so D rejects C so it can hold E's proposal instead. Once again, C needs to propose to someone. The third person on C's list is E, who now holds C's proposal. F then proposes to its top choice, B. Not only does B prefer F to its current proposer, A, but F is actually B's top choice too. As they both prefer each other to everyone else, no one else can disrupt their proposals. Of course, A is rejected and now needs to propose again. Second on A's list is F, who of course rejects A in favour of B. Finally, A successfully proposes to C. All members of the group now hold a proposal, and so we can move on to the next stage of the algorithm. In the removal stage, the preference lists of each group member are cut down according to who is holding a proposal from whom. A member, Y, is removed from the list of another member, X, either if X prefers the member it is currently holding a proposal from to Y, or if Y has removed X from its list. In practice, this is quite simple. First, we update A's preference list. A currently holds a proposal from D, who is fourth on its list. As D already proposed to A will never have to accept anyone further down its list than D, and so the only member below D, E, is removed from A's preference list. As A will never accept a proposal from E, we can also remove A from E's preference list. Next, we move on to B. B currently holds a proposal from the first member on its list, F. This means that all members below F can be removed from B's list. Again, as B will never have to accept a proposal from a member lower down its list than F, B can be removed from the lists of C, A, E, and D. C currently holds a proposal from A, who, following B's removal, is the last member in C's preference list. Therefore nothing is removed, and we move on to the next member. D currently holds a proposal from E, which allows for the removal of C and F from its list. Of course, D is then removed from C and F's lists. Next, F, the only member below C is removed from E's list, and E is removed from F's list. Finally, F holds a match from its top choice, B, and so all other entries are removed from the list, as F is removed from theirs. Now all the possible removals have been made, we can make a new table using each member's reduced preference lists. While we have greatly reduced the number of possible matches for each group member, the set of stable matches has not yet been found. To achieve this, we need to use rotations. In this stage of the algorithm, we write out a sequence of tuples in this form, using XO as the first member in the table that has more than one member left in its list. As shown, the sequence is formed with YI as the first member on XI's preference list, and YI plus 1 as the second member on XI's preference list. As it is necessary for XI to be last on YI's list for YI to be first on XI's list, XI plus 1 can be found through being the last member on YI plus 1's preference list. While generating this sequence of tuples, we identify any repeated subsequences of elements and call them rotations. This is a lot to digest at once, but in practice it is far simpler. Let's start with A. Following the definitions, the first element of the list is AC, as A is the first member we come to with a list with one or more members left, and C is the first element on A's reduced preference list. The second element is ED, as D is the second element on C's list, and E is the last element on D's list. The second element on E's list is C, and the last element on C's list is A, giving the tuple AC. Here we have found a repeating subsequence, or a rotation, written A, C, E, D. Now we have this rotation, we can use it to further shorten the members' preference lists. To begin this process, YI needs to reject XI's proposal, so XI can instead propose to YI plus 1. This will then set off a chain reaction of activity, as you will see. In our example, C needs to reject A, after which A is left without a held proposal. A must then propose to the next and only remaining member on its list, D, who prefers A to its current match E. D accordingly rejects E and leaves it to propose to the only remaining member in its list, C. As C is no longer holding any proposals, C holds E's proposal. This leads us to a second round of removals. A is currently holding a proposal from D, its last choice, and so nothing changes. We ignore B, as we do with F, as nothing will be removed from a list of one member. Next, C is holding a proposal from E, and so A is removed from its list, and C is removed from A's list. D holds a proposal from its first choice, A, and so we remove E from its list, and vice versa. This leaves all of the remaining preference lists with only one member, and we arrive at our solution. If there were more members left in the preference lists, then we would have to identify and remove more rotations until we reached one member in each list. As you can see, all of the members now hold a proposal from the member that holds their proposal, forming a set of 3 stable matches: A and D, B and F, C and D. On this solution, the algorithm terminates.
In the first phase, there can't be more than n squared proposals, since no one ever proposes to the same person twice. The computation required for a proposal is bounded by a constant, so the complexity of the first phase is bounded by n squared. The rotation phase has a complexity which is bounded by the number of eliminations times a constant. There can't be more than n squared eliminations, so the rotation phase also has a complexity of n squared. This means that the algorithm as a whole is O(n) squared. If you want a more in-depth analysis or proof of this, there's a link to Irving's original paper in the description, which should contain all the information you might need. Thanks for watching our video, and if you have any questions, please leave them in the comment section.